We can if they unmute.
Oh, yeah, they're muted, yeah.
Yeah, I can talk if you want.
申します。こんばんは。今日はですね、機械学習の論文の一つ紹介いたします。でも英語で話させていただきます。My name is Nijkamp. For those who don't know me, I joined the company last year. I originally came from China. My personal interest is machine learning, actually mathematics. But machine learning is kind of like this field that bridges mathematics to programming. Such a wonderful field. So I just got into it, can't get enough of it. Spend my part-time doing reading papers in machine learning. So today I think I'm gonna share one of those papers. I have to admit that last time I shared a paper, it didn't go so well. Yeah, I've been thinking about it. First thing, I went over the time limit. So this time I'm using Rabbit Shocker to make me under 10 minutes. Secondly, I will not go into too much of the technical details. I think I really want to share the general idea because a lot of people do not, who do not work, well, even including me, but I spend more time on it, so I know some of the jargons. There are a lot of gibberish if you do not know the background. So I think I will spend more time introducing the background and conveying the general idea. I think that will be useful for the audience. And just I prepared an appetizer so that the particular, there are so many models and methods these days in machine learning. The model I'm going to introduce today is called EBM, energy-based model. And like this model, after you learn it, you can actually start from this completely noisy signal. This is like uniform distribution, it's all signal. And you can gradually from those signal to generate the images. Well, you learn, and it's not identical to the images that you originally learned, but you also can generate the images that kind of similar to what you learned. So I think this is kind of fascinating. You might have heard the name of GAN. It's like a different method, but achieves the similar result. It can generate, maybe you heard the word deep dream, like it can generate those things that you've never seen, weird pictures. Well, this is another method. It's kind of like GAN, but it's based on different perspective, and it's called EBM. So the name of the title, oh, sorry. Yeah, so the title of the paper is on the anatomy of MCMC-based maximum likelihood learning of EBM. So that's what I talk about. EBM is the last part of it. I think I will spend a lot of time just introducing some of the terminologies here so that we understand the background. So energy-based models is, like I mentioned, is just different way, kind of similar to GAN, but it's based on something called energy. Well, it's kind of like a jargon, but you can just think of energy as probability distribution. Why they call it energy is because probability distribution, well, probability lies in the interval of 0 to 1, right? But if you take the logarithm of it, then it became 0, well, it became minus infinity to 0. But then you flip that logarithm, then it becomes plus infinity down to 0. So that's what energy is. And also a little bit different from probability distribution is it does not need to come inside 0 to 1, because in real, well, the general idea is when during the learning time, every picture that got fed to me, I'm trying, well, they are just like a very long vector. Like if the picture was 4K, then it's a vector in 4K space, right? And I try to learn the probability distribution of all the pictures that I was seeing. And those probability distributions, I kind of call it like energy. So it's energy-based models. It's a generative model and some unsupervised model because those pictures do not come with labels. You just see those pictures. It's a generative model because you learn the joint distribution of all the pixels in it. Like I learned the joint distribution of pxy instead of px under the condition of y equals smaller y. that's what this method is based on. And once you learn this probability distribution, then in inference time, or after you learn the model, after you train the model, you're trying to use it. That's called inference time. And during that time, you just start from anywhere in this like 4K dimensional space, anywhere, like what we just saw at the beginning. You start from a noise picture, and you start walking. You start walking toward those so-called low energy areas. Then you can hit something visible. Those low energy areas correspond to high probability areas, because remember, energy was like the negative logarithm of probabilities. So that's the entire idea of this method. So that explains this part. Then what is MCMC-based maximum likelihood learning? Well, it just turned out that the difficult about this particular method is during training time and also the inference time, it's hard to sample from the probability distribution that you learned. So people end up coming, I think it's a paper in 2019 that you can use MCMC to try to just grab a sample point out of the distribution you learned. And what is MCMC? It stands for Markov Chain Monte Carlo. So Markov Chain is pretty easy to understand. It describes a chain of events that every event happening, the probability only depends on the event before it. So for example, like in onboarding state machines, we're currently in the state of some merchants submitting their application. And if it was a Markov chain, then I say the probability of this state transition to being rejected only depends on the current state that is pending. It does not depend on all the prior states of how it became pending. Like before, it was in a draft state, then became pending, then back to draft, then became pending. It doesn't depend on those. That's what Markov chain means. So for example, when this application was pending, it has a 60% of probability to get into rejected and 40% of probability of staying where it is. It adds to 1, so it's a probability, and that's what Markov chain. And Monte Carlo is just a simple jargon. It just means gambling. Yeah, so Markov chain, Monte Carlo, because Monte Carlo, I think, is a famous gambling city, right? Markov chain Monte Carlo just means that I construct a Markov chain which has, and I just keep on walking down that Markov chain based on the probability, and with the presumption that the Markov chain has the same probability distribution of that probability distribution that we just learned, which is hard to sample. It needs to have the same probability distribution in its equilibrium state, so that this hard to sample probability distribution can become easy to sample, because Markov chain Monte Carlo is such a doable operation. That's the idea. And what else the jargon in it? Maximum likelihood learning. Yeah, that's also a easy jargon, just like Monte Carlo. That basically means that I want to learn a probability distribution. Well, in its most formal definition, it means if I have a parameterized probability distribution and I saw a bunch of data and I want to find the best parameter so that the data I see is most probably generated by this distribution. It basically means I saw a bunch of data and I try to find a probability distribution that can most probably generate those data, right? So that's what it means. I probably spent too much time on the first slide, but the turtle is there already. So what this paper discovered is this method is not so easy to converge. They're non-convergent learning process like this one. It tries to learn this flower, but it learns too much. The distribution just became something like this. It learns too much. It doesn't converge. The energy becomes too low, which means the probability is too high. It's just overlearned. And another case is a convergent ML, which is the good case. The iteration means after I learn so many times, it basically converts to a stable state. So the paper discovered that there are 2 cases using this method. And think we're going to skip a lot of details and just look at the pictures of this paper. So first of all, it made a toy example. And this toy example really convinces you that this thing really happens. It is toy because it only has 2 dimensions. That's the reason why we can visualize it on the screen. The first dimension is this axis. The other dimension is this axis. And the distribution, well, it first make a ground truth, right? The ground truth was, as you can see, as you can guess, this is the accumulation of 8 Gaussian distributions all merged together. And they tries to use this method to learn this distribution. And there are 2 outcomes based on how you tune those hyperparameters. One outcome is you learn a non-convergent ML, which means the density you learn just focuses in here. All the other densities you didn't learn, right? This fails basically. And this KDE is a different method of learning of maximum likelihood learning. It's called kernel density estimator. It's just for comparison reasons. It should have been learned in this way. And on the other hand, the successful learnings can successfully learn those distribution. It can learn those 8 modes of this Gaussian distribution. Well, you can basically ignore this rule because it just takes the logarithm of the original distribution. And this is another toy example. This time, instead of accumulating 8 Gaussian modes, I think this time it, I forgot how it was constructed, but this is also a toy example. Like when it didn't learn successfully, only learns the outer circle and didn't learn the inner ones. So by using this toy example, well, you can really be convinced that this is really something something objective. It's really there. Because otherwise, maybe it's just you. Well, in the previous picture, we saw that it becomes stable, but maybe you just didn't run it long enough. Once you run it long enough, maybe it will then destabilize. But in that toy example, I think the author just proves that this thing really exists. This probably the last slide that we can see in this presentation. So then the author moves to a more real example, but it's actually not that real. Those are just, I looked at the source code. It's all 32 by 32 with 3 channels. So it's probably 20,000 dimensions at most. So it's no match for any real world application. This is still a toy, but in the author's eyes, this is not a toy anymore. And you can see there are like 2 cases. Like one is the failed learning and the other is successful learning. So the contribution of this paper is the author will tell you what to look for, what diagnostic numbers to look for in order to make your learning successful. And we can jump to the very last slide now. Yeah, so this is the main contribution of this paper. It basically tells you that this particular method, you can analyze it in 2 axes, whether it's convergent or non-convergent. And the other axis is energy difference, which means the learned energy and the true energy, what's their difference. If during the learning process, you see that value oscillating, or you see the value contracting or expanding, that both means it's a bad case. You will have either vanishing gradient or exploding gradients. And the good cases are in the middle. You need to watch for your energy difference during the training process to make sure that is oscillating. And then in order to make, during this, then you're in the good area. And if you want to make your learning really successful, then there are some further technical details about how to do the initialization in order to make your learning converge. Yeah, that's the idea. Thank you. Questions? I can later send the link to the paper in the channel, but here's the original paper. Basically, looked at the first graph on first page, that's the main contribution of theirs. And here is what to look for during the training phase. You will see that the energy oscillates, which means good, but if it didn't, which means bad. And this is the graph we looked at previously. This is the different one. The author did 3 experiments. and basically just tell you how to make it successful.
What is the update algorithm?
I'm sorry.
What is the update? What is the update algorithm?
Update algorithm.
Is it CD? Is it CD1?
You mean update of
Yeah,
what?
the update the weights.
Oh, yeah, it's just gradient descent. Yeah.
It's gradient descent, okay.
Yeah. I actually forgot to mention an important part is the loss function. You have to define the loss function, and during the training phase, you would try to minimize that loss function, and the direction to minimize it is the gradient descent. But the algorithm is actually a little bit different from ordinary gradient descent. This is the algorithm. It's basically a 3-step loop. You have those x plus i's are the images from the training set. You got those images, and then you try to look at the distribution that you learn, which is those y's. You try to draw those images from y, and this process is the MCMC process that we just described. It has this random force in it, random direction in it, which makes it Monte Carlo. It's just gambling, right? It tries to walk down this Markov chain to trying to sample just try to obtain a sample from the distribution that you learned. And the important question that David asked is this loss function. The loss function was defined here. Like we mentioned in the title, it's a maximum likelihood learning. So the loss function very naturally would be defined as the distance between the real probability distribution and the probability distribution that you learned. And the distance was using the KL distance, which is just widely used, Kullback-Leibler divergence. And the author just expanded mathematically until this step where it made a approximation to turn it into an actionable algorithm. Otherwise, it wouldn't be able to calculate computationally those expectation values. So this is the loss function. That's the most important part. Yeah, I think David asked a great question. Thank you.
So basically it's a neural network, and it's a matrix. And in order to make your image, you update it until it reproduces your image, and it comes up with 4 probabilities where you sample them, so the chances of it getting the image is higher.
The Monte Carlo from the Markov Chain Monte Carlo, is that, like, what is the sample there? Does it just take, like, what's the mechanism of the sampling? Is it purely random, or is it just based off the Markov Chain result? Like,
oh, that's a very good question. Yes, it's based on the Markov Chain result. See, the general idea behind this is it is really hard to sample the distribution that I learned, because I represented the distribution I learned using a fucking neural network. How do you sample something from that? Right? So this is really a breakthrough. Otherwise, the method won't work. That is in 2019, I think, probably a paper by OpenAI. I think they got their idea from physics, because the key idea is to construct a Markov chain, so then the Markov chain has the desired distribution as that neural network represented distribution. And the way you walk down that Markov chain is you take 2 directions. One direction is you look at the loss function and to find the gradient descent direction. The other force is a random force, so that you well, it's kind of taken the idea from physics, because if you put a pounder inside the water basically receives 2 forces. One force is one force is proportional to the speed of the particle itself. The other force is some random force. So he took that idea and let this particle just walk down the road. And that Markov chain constructed just has the same equilibrium distribution as the learned learned distribution. So by walking down the Markov chain, you can just obtain a simple, and that critical process is used both in the training time and in the inference time, because in training time, you need to look at how good the probability distribution that you learned in order to calculate the loss function. The loss function is between the learned distribution, the distance between the learned distribution and the real distribution. And after training, in inference time, you need to use the same process to just fetch a sample so that you can generate images. Yeah, so it's a really critical process and use both parts.
Is it Gibbs? Is it Gibbs?
Oh, right. Oh, David really knows this. Yeah, it's Gibbs. Gibbs.
Was it Metropolitan or something? Is the other one?
Yeah, there are lots of ways to construct the Markov chain. The particular method used by this paper was called Gibbs. Yeah, Gibbs something. No. Gibbs-Boltzmann density was well, this is a way in the original part of the paper where the idea comes from. Well, you need to construct a probability distribution, then you need to parameterize it. And the way they parameterize it is by follow the Gibbs-Boltzmann distribution. Gibbs-Boltzmann distribution is a distribution to describe a particular physical system to appear in a particular state, like in a pound of gas, whether this particular pound of gas obtains a particular temperature with a particular state. It just describes the probability of this physical system appearing in this state. And they just take this idea into the realm of machine learning. And basically they just replaced this part by a neural network. In this particular case, a convolutional neural network, because it's dealing with visual signals.
Well, the basic idea is neural network can be thought of as a bunch of mountains and troughs, and when you initialize it randomly, it starts off as just a little crumpled piece of paper, but as you train it, there's mountains and troughs. And sampling gives you, basically just has you put a point some random place and see which trough it falls into, and that's the picture you get out.
Yeah, that's the animation that we originally saw.
That's how you get the animation. You basically initialize it randomly, and that's basically a point randomly somewhere over the mountains and troughs, and it drops into one of the valleys, like it drops into Pisa Valley and creates.
Yeah, that's the essence of
Has
it.
like a value associated with it.
Yeah.
Or like an image, I guess, a category.
Yeah, it's a.
Well, it's a manifold, right?
Yeah, it's a manifold, but you can think of it as a valley in some dimension.
Yeah, it's a manifold because they want to make it differentiable so that you can use gradient descent to.
Exactly, and the energy is and if it's a low energy, then it's not.
I need another beer, I think.
I think it's time to wrap it up, and then maybe you talk.
Yeah.
Yeah, why don't we grab
Nice.
Yeah.
Okay, thank you.